Hello everyone, welcome back to the topic of the member stiffness matrix, and this is dealing with trusses. Again, we said that we have three elements or three structures that we're dealing with during this semester: trusses, beams, and frames. So all these lectures are being targeted towards trusses. As we mentioned earlier, that we are going to be labeling all the members and the joints or the nodes, and we have that code number that we have, and then we're going to establish the element stiffness matrix and then the global stiffness matrix for the structure, correct? And the way we do some sort of transformation between the local coordinate systems and the global coordinate system is going to be using transformation matrix. So we have a transformation matrix for forces, we have transformation matrix for displacement. What do I mean by forces? What I mean by forces is that from the local forces along the member to the global forces of the structure, and also matrix for the local displacements of the member to the global displacements of the structure. So this is very important for us to understand. And to give you an idea of what I'm talking about is basically here are small delta 3 and delta 4 and delta 1 and delta 2 in green color are called the local deformations. The blue color, big delta 1, delta 2, delta 3, delta 4 is the final global deformations of the whole structure. So there are some transformation for this. So before we get started and get this transformation, we need to know that there are steps that we need to follow. Establishing the local stiffness matrix of the member itself. So we need to establish the stiffness matrix of the member, and that will be as force equals K times delta. This is one specific case that we're having. It can be written down in this case, or it will be kind of reduced to 2 by 2. So it can be ideally 4 by 4, which is 4 degrees of freedom, or 2 by 2, as you can see right here, because the rest are zeros. This is a truss member stiffness matrix in the local coordinates. What do you think you should do next? Transform that. So this is what we're going to be doing, which is transforming that. And these are the relationship, the equations that is relating the displacement in the local coordinate system to the displacement of the global coordinate systems between this part and that part. And that will be using this transformation matrix. So basically we're saying that the local displacement, this is a transformation matrix, and this is the global displacement. That is exactly what we're talking about as far as the coordinate transformation matrix. We need to do the same thing also for forces, and then once we do this, then we can assemble all this into the final stiffness matrix of the structure itself. And the final one, this is the K, the big K, that will give us an idea of how can I find the displacements and how can I find the deformation. So let's say this is your stiffness matrix in the global coordinate system. And basically it looks, the final equation looks as the forces in global equals to the stiffness matrix of the whole structure multiplied by delta. And that's it. That's all what you need to do for this. The way we do it is we partition this. You see this dotted line that you see right here? This is the partitioning that we're having right there. And the partitioning is telling you that there are unknown displacements and there are known displacements as well, correct? So let's say that these are the unknown displacements and these are the known displacements. And there are known forces, these are known forces, which are these two, and then the unknown forces. The beauty of this partitioning is telling you that you can use this small matrix, F1 and F2, which is the known forces, equals the small matrix of K multiplied by this delta, which is unknown. So if this is known, as far as known forces, and the K is known, and this is unknown for displacement. You can find the displacement. Then you can use this in order for you to find the forces in the next step, as you can see right here, to get the member forces and get the support reactions as well. That's what I wanted to share with you, how to do this step, and this is very easy and very straightforward, and we are going to share an example, and that example is how to establish this stiffness matrix. I might just do that as a homework so that you can do it, and I'm going to post the solution afterwards. So let me just share with you what I'm talking about. That's basically an example, as you can see right here, and I'm just going to ask you to do this numbering for the members, numbering for the nodes. So you have the member 1, 2, 3, 4, 5, and you have the nodes, and then you are going to do what's near and what's far and start establishing the stiffness matrix for the member, and then the transformation, and get the stiffness matrix for the structure, and you will be able to identify the displacements and the forces developed in the structure. I hope that helps, and let's see the following session. So I believe that we're going to have like 6 or 7 sessions just for trusses and some examples before we move on to beams. So we are not going to move to beams unless if we feel confident doing this hand calculations in trusses, and do as well the software that you're going to be downloading very soon. Thank you so much, and we are going to be meeting another time to identify any problems that you're having, and that will cover basically the first few weeks of the semester dealing with trusses. You guys have a wonderful day, and I'll talk to you soon.